Hi, everybody. Today's lesson is for Friday, April 24th, 2020. I hope you guys are all doing well, hanging in there in this home stretch to the end of the semester. I'm filming this on the Sunday before that Friday. It's the 19th, and I just wanted to share with you guys a fun fact about today. We discovered Jeanette's new favorite musician is Jimmy Buffett. So anyways, if you are listening to Cheeseburger in Paradise, think of our little bouncing baby pineapple. At any rate, let's go ahead and get to the notes. Just a couple quick admin things, and then we'll do a quick overall concept review for the final exam. All right, so the first thing I'm going to do, here you can see kind of our traditional intro admin, last time goals for today. I'm actually going to go ahead and share my screen to the Google form that I sent out the other week. Thank you to everybody who responded, and I apologize, I sent that a bit before we got sort of word about how we had to administer the final exam. So I apologize for kind of giving an option and then having to make some adjustments. But overall, thanks. It sounds like everyone is very flexible with respect to a question and answer session. People are feeling good, and a few people prefer Monday over Wednesday afternoon. I'm thinking if it's okay with you guys, I'd like to have Monday's class be synchronous. I'll send out an email to follow up on that, just to also make sure that we wrap up all of the needed sort of admin things for the course in terms of student opinion forms, kind of getting you guys, a chance to answer questions. I think that'll also be a good opportunity. I'm going to try to record that session. So if you want to go back and watch that while you're studying, that's totally fine. I also realized, there's some time between Monday and Thursday. So I think it would be helpful. I'll plan on signing on Wednesday between 2 and 3 p.m. Eastern. And why don't we go ahead and just sort of have, both of those times be sort of question and answer as needed. And I'll be available. If you guys are feeling confident though after Monday, no need to sign on Wednesday. That's just, an additional time that you know where to find me. And of course, feel free to reach out via email at any moment. Again, I apologize about kind of some of my confusion with the exam. I think we're required to hold it between 9:30 and 12:30, on the scheduled date on mid. So I will go ahead and plan on that. I'll give you some more details in a moment, and then we can talk more on Monday and Wednesday if you have any specific questions about content and things like that. In terms of schedule, this list is getting quite short. So today, this video lesson is going to be primarily a review for the final exam. It shouldn't be too long, so please also keep plugging away on project 2 with your partner. Monday, we'll do course wrap up. Again, if it's okay with you, I would like to have that class be synchronous. Let me know if there's an issue, time zones or, other work that is sort of like last minute things that need to get done. Just send me a note and we can, discuss that in more detail. And then Thursday is the final exam, and then project 2 is officially due by Thursday. If you're finished with it beforehand, welcome to submit early. Again, goals for today. For this video, we're really just looking at some of the main concepts, my proposed format for the final exam. And again, please don't hesitate to let me know at any time if you have questions. So let's go ahead. And this is sort of our last, day of note-taking. Sorry for getting a little blurry there. So this will be a brand new subheading of our sort of outline format, final exam. And the first, I'd like to give you guys some general info. Per ACDEAN instructions, we are required, so we must hold exam at scheduled time in mids, which for this class is Thursday, 30 April 2020, between 9:30 to 12:30 Eastern Daylight Time. So that is the big date to keep in mind. I think the tentative plan is I'll have the exam go live at 9:30 that morning. And please make sure you submit it within that 3-hour block. And you can submit it again, same format, either Blackboard, email, or Google Classroom. Since we had a bit of an issue last time with Blackboard, if you do submit it via Blackboard, please also maybe send it to me in an email just as sort of a backup. I'd really appreciate that. I also want to emphasize that if you have an issue with this time being, impossible. So for example, if you are in a time zone that makes this like a ridiculously early time to wake up, or if you have, another commitment like in the morning due to family commitments or other commitments, I know there's a lot going on right now. Please, so with time, please email me ASAP. I really don't need any details other than your company officer's name and the time that you would like to make up the exam. If you can take it sometime on April 30th, that would be great. But if a later date is better, that's also fine. So I would just need your company officer's name and proposed time to take the exam. And then what I can do is I can fill out something called an exceptional request form, which is just a form that I can submit to the acting so that we can like officially reschedule your exam. So please don't hesitate to reach out to me if you have an issue. I know this is kind of creating a bit of a difficult situation for some folks. So I really appreciate you guys hanging in there, and I'm really happy to help however I can. So just keep that in mind. In terms of content, I'm going to say that the exam is going to be cumulative, but I'm putting that in quotation marks because I think you guys have already done a fantastic job showing me that you know the material from exam 1 and exam 2. So the direct stiffness method, STAD, API design checks, no big picture concepts. So no big picture concepts from exams 1 and 2, but the majority of the material will be from kind of the things that we talked about after exam 2. So larger percentage of questions from environmental loading. And specifically, we focused on wind loading and then wave/wave plus current loading. The format in terms of what to expect, it should be similar to the practice exam and similar really to exam 1. In practice. I think exam 2 was a bit long. Since we have to have everything done in about 3 hours, I want to make sure you guys have time to, scan and upload, to take your time to double check your answers. So expect maybe a slightly shorter exam than exam 2. So, closer to, what you did in class during exam 1. So kind of with that in mind, expect maybe 4 to 5 FE style problems. And then 1 to 2 multi-part free response. The exam will be open note. So again, feel free to look at any of the resources that are posted on Blackboard, Google Classroom, but please make sure that, all work is your own. So please work individually. And I will also, again, I really encourage you guys to make an equation sheet. I think that that can be really helpful. I know we have though a lot of like tables and sort of the large equation sheets from waves. So I will compile and post some of the main figures, tables from handouts that we've used. But that being said, definitely I encourage you to kind of know where things are and be able to reference things, you know, sooner than later. Also, I wanted to, you know, make sure that I'm available during that time if you have questions. So I'll plan to have like a Google Hangout if you have questions. On 30 April from 9:30 to 12:30. So please, you know, jump on if you have any questions about what I want you to find. So please jump on to clarify questions. Again, I can't really tell you, you know, like how to solve a problem, or I can't really like clarify part of the solution, but definitely if you're not sure what I'm asking you to solve for, you know, that's a perfect time to jump on and, you know, I'm happy to explain that. Let's go ahead and talk about what big picture concepts that we've talked about, you know, for the past semester. So this will be big Roman numeral 2, big picture concepts. So I think, you know, we've spent the vast majority of time talking about the direct stiffness method, so that we can find displacements and reaction forces for statically indeterminate axial bars, axially loaded bars. Then we added complexity, another degree of freedom in trusses. And then finally talking about frames, which includes, you know, everything, horizontal and vertical translation as well as rotation. I think you guys have already showed me on exams 1 and 2 that you can, you know, do these big giant problems. So now really what I want you to focus on is the framework and maybe short calculations of, you know, an individual stiffness matrix here or there. But again, I think you guys have done a great job on the first couple exams. So I would say focus on the framework. So for example, if I give you some sort of frame, you know, and let's say it looks like this. You've got maybe something there, maybe a roller support here, here. And so we have, you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 bars. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 nodes. So how many individual stiffness matrices do we need? We need the same as the number of bars. So 15 individual matrices. Each individual stiffness matrix is how big? We know that there's 3 degrees of freedom at any node. We can have horizontal translation, vertical translation, and then rotation. So it'll be 3 degrees of freedom at each node times 2 nodes per bar, so 6 by 6. And then how big is our system? Is going to be 3n by 3n. So if we have 12 nodes, in this case, it'll be 36 by 36 for a 2D case. You know, make sure you can write the boundary conditions at any node. And that may include something like a fixed end force and moment, or which, remember, are not applied as boundary conditions. For a frame, we have our system equation written as our force vector is equal to our system stiffness matrix times our displacement vector plus our fixed end force and moment vector. So that's for a plane or for a frame. For a truss, it's a little bit different. We only have 2 degrees of freedom in each bar, and we're not going to be dealing with fixed end forces and moments. So, you know, just have a look at those. I think we had, you know, kind of some reviews on those before exam 1. Again, also just be able to write maybe part of individual stiffness matrix for trusses, axial bars, and beams. Probably the beams would be in local coordinates. I think you've already shown me you can do global coordinates, and if you can do local coordinates, you can do global coordinates. It's again just following that roadmap from our equation sheet. And then also, using Battleship. So putting together the system stiffness matrix and system equation. Those are kind of the big takeaways from the direct stiffness method. Related to the direct stiffness method, I think, is STAAD concepts. I think you guys have done a great job. I know a lot of you have been working on STAAD for the project, which I'm really psyched about. Thank you. And I think you did a great job in, homework 6, exam 2, sort of, again, showing me that you know what you're talking about when you're doing STAAD. So good work. In terms of STAAD, again, process, big picture, and general questions. I think if you're focusing your studying, I would focus studying more on, direct stiffness method, API, environmental loading, and just sort of general STAAD processes. You're probably not going to have to fill in any dialog boxes, with very specific details or anything like that. So after STAAD, we talked about API design and sort of checks. And make sure you know how to do each of the 5 checks. Again, I think, say do the whole API design is maybe too long for this exam, but I might ask you to do any of the axial, bending, shear, hoop, or combined check. And again, we've had a couple problems where maybe I don't tell you all the information about the structure itself, so you need to sort of back calculate. So for example, if you're given your compressive load, P max, find the maximum length. Given an allowable stress, so for example, an allowable axial stress, find P max. Same with bending, shear, hoop, combined. Given, or maybe find your hoop stress, your actual hoop stress, and your allowable hoop stress, and using those factors of safety. The P delta effect, when is that important? What does it do? Kind of, etc. So make sure you also are familiar with kind of how to back calculate some of these problems. And that really brings us to the last main topic for the course, which is environmental loading. So let's go ahead and start a new page. And this will be letter D, environmental loading. And we've really focused on 3 types of environmental loading, but kind of you can lump current and wave together. So if we're really breaking this down, we're going to talk about wind loading and then wave/wave plus current loading. So important things for wind loading, we've had to find our design wind speed. We had to do that in the project. So we had to first use our figure 3.3 or 3.2 to get our 100-year wind speed based on location. Depending on if you're offshore or not, you might have to apply an amplification factor of 1.1. And then also you might have to apply a gust factor to account for any resonance that occurs between the wind gusts and the pylon. Again, if you don't know the gust factor, if no one tells you, you can assume that the gust factor is equal to 1.2 if no other information is given. Also, we've calculated the wind load on platforms, buildings, piles, even incline structures. And that's all based off of this drag force equation. F sub D is equal to 1/2 times the density of the fluid, so in this case, probably air, times our drag coefficient, times U squared, our wind speed squared, times our projected area. I think the things to be careful of in this equation is make sure that U is in feet per second, so you might have to convert from miles per hour. And also be careful with how you define your projected area. Remember, that's the area that's exposed to wind. So for something like a pile, it's the pile diameter times the exposed length. For something like a building, it's the face area of that building that's exposed to wind. A platform's a little bit different. You'll see some sort of leading word like open platform, grading, wind can flow through the platform. I'll give you, lots of kind of clues like that. Then you have to sum the sides of that entire platform. So be careful with how you define the projected area. That's really it for wind loading. And so then the very last thing let's talk about is wave loading. Kind of the first part we had about that was if I give you some wave properties. So given our wavelength, find our frequency, omega, and our period t, which is equal to just 2 pi divided by the frequency. Also, at a given depth and time, solve for your water particle velocity, your water particle acceleration, also finding the drag force, the inertial force, and then summing those together to get your total force per unit length. Remember that your total force per unit length is in a unit of pound per feet. So if you want to sum that, we're going to have to use Simpson's rule, which we'll talk about in a second. There were a couple examples in the homework and also the practice test with 2 or more piles. So just as a quick example, if I had 2 piles, here's the ground, here's the water, here we have x is equal to 0, and here we have x is equal to x. Maybe my wave crest is at pile 1, so can you find the phase, which is just solving for omega t in our equation for eta? And then also, can you find eta at pile 2 at x equals x, as well as other properties? I also wanted to do a quick example of using Simpson's rule by hand. I know we were able to use a spreadsheet, but I also asked for sample calculations in the project using 5 endpoints for segments. So for Simpson's rule, let's say that I had some pile and I had a 100 pound per foot load here, and then an 80 pound per feet, 75 pounds per feet, 72, and then at the base we have 70 pounds per feet. Again, here is my pile. It's not just floating in space. We can assume it's anchored into the ground, and that maybe it extends right to the still water level. And if all of these segments are the same, let's say 20 feet apart, we can apply Simpson's rule. So our equation for Simpson's rule is that F total is equal to delta Z divided by 3 times the summation of my force at whatever location times the Simpson multiplier of that force. And again, our pattern is 1, 4, 2, 4, 1. So if I plug in numbers here, this will equal 20 feet over 3 times 100 pounds per foot times 1 plus 80 pounds per foot times 4 plus 75 pounds per feet times 2 plus 72 pounds per feet times 4 plus 70 pounds per feet times 1. And so plugging my numbers into the calculator there, I got 6,187 pounds. And if I want to find the location where this acts, I can use moments to find Z resultant from the still water level. So I can say that Z resultant is equal to the summation of my force per unit length at a given location times the Simpson multiplier for that force times my depth at that location divided by the summation of Fx sub I times Simpson multiplier sub I, so this value here. So plugging in numbers here, this will equal, so our first force is 100 pounds per feet times 1 is our Simpson multiplier times our depth is 0 feet, so that's going to be 0. Plus, next we have 80 pounds per feet times 4 is our Simpson multiplier times negative 20 feet. Plus 75 times 2 times negative 40, plus 72 times 4 times negative 60, and then finally plus 70 times 1 times negative 80, all divided by this quantity here. So we have 100 times 1 plus 80 times 4 plus 75 times 2 plus 72 times 4 plus 70 times 1. And plugging in numbers here, I get that Z resultant is equal to negative 38 feet below the still water level. And then just for completeness, I'll put Morrison's equation up here. That's, I think, kind of the last major equation, and then, you know, referencing, of course, the waves equation sheets for U, A sub x. Remember our Morrison equation for finding each of these individual force per unit lengths. We have lowercase f sub x is equal to our drag coefficient times our pile diameter times 1/2 times our fluid velocity, now we're in water, so 1.99 slugs per foot cube, times our water velocity, times the absolute value of that water velocity. Remember here to make sure that you include the current if there is one. So this will be U wave plus U current. If there is not a background current, U current equals 0, and so it's just the water particle velocity from your waves equation sheet, but make sure to add in that current if there is one in the problem statement. And then the inertial contribution will be our mass inertia coefficient, C sub m, usually said equal to 2 times rho times pi d squared over 4 times our x acceleration under the wave. So this is definitely an important equation to know. Again, your units here are going to come out to be pounds per foot, which is why we need to sum them over the length of the pile or integrate them over the depth in order to find the total wave force on the pile. So again, let's plan on having kind of questions about either homework aid, exam, the practice exam, any of the previous exams, any of the previous homeworks. Happy to talk about in Monday's class. I wanted to say thank you guys. You know, one real class left. It's definitely been a crazy end of the semester, but I really appreciate you guys sticking with it. And, you know, it's been, you know, a great semester, and I'm really excited to see you guys hopefully in person in the fall. So have a great day and a wonderful weekend.